Our presentation is on fine-tuning and enhancing performance of our Spark jobs. We all come from IBM and are data engineers. We're going to touch on a wide range of topics for our presentation that we tune to get our application running as quickly as possible. So a little bit of background. All of this work was done for a data validation tool for ETL. It's running over 2 billion checks across 300 different data sets. Those checks are on completeness, data quality, and some others. Initially, our job was taking over 4 hours to run for 9 months of data, and that was if it ran to completion. Quite often, we'd see out of memory or other performance issues. We had a challenge to get our runtimes down to an acceptable level and also have our stable runs. So with that challenge, we did months of research and got the same application running in around 35 minutes for a full year of data. Some of the tricks we did were we moved all the processing to in-memory, which greatly improved our runtimes. And then we're going to talk about some of the other tricks as well. One thing to note is we developed all of our applications using Scala, so all the examples will be in Scala. In tuning, we dealt with many different facets, including CPU, parallelization, garbage collection, and so on. So these are all different configurations you can tune and tweak. One thing that you want to make a note of is that when you tweak one, you are going to affect others. So for example, if you increase the amount of memory per executor, you will see increased garbage collection times. If you give additional CPU, you'll increase your parallelism, but sometimes you'll see scheduling issues and additional shuffles. What you want to do is anytime you're changing one, see how it affects the others and use the monitoring you have available to you to verify all of your changes. We use sparkui, Sysdig, and Kubernetes metrics. Skew is one of the easiest places you can see some room for performance improvements. Skew just means an uneven distribution of data across your partitions, which results in your work also being distributed unevenly. One thing to note is that your applications will always initially have skew issues, especially if your data ingestion has skew, then the rest of the application will as well. One extreme example is if you want to do a filter on some data, and one partition had 2 records while the other had 1 million. The stage with 1 million is going to take significantly longer than the stage with only 2. This is looking at some examples. So the first example is us looking at sparkui. Notice that the vast majority of stages completed quickly, while the remaining stages took significantly longer, in some cases 6 times longer. This is a great way to identify skew, is some stages completing quickly while others take way more time. The second screen capture is looking at system metrics, and notice that some of the executors are taking way more memory and CPU than others for the same stages in the job. So if you think you have skew, it's really easy to confirm as well. So one way is looking at your Spark logs. If you look at your RDD partition sizes in the logs, you'll notice that on the left side, the same RDD, some partitions have only 16 bytes of data, while others have hundreds of megabytes. On the right side, they look much more evenly distributed. Another thing you can do is using the data frame RDD API, you can print out the number of records per partition to confirm that there is skew. Again, on the left side, you'll notice that some partitions have over 1 million records, while many have 0. And on the right side, we see a much more even distribution again. So once you identify skew, what are some ways you can handle that skew? One of the most naive approaches is the blind repartition. It can also be very effective, though. Where you want to use repartition is, for example, if you want to increase the number of partitions you're using for large operations, or if you're reading from a partition source that has less than the desired number of partitions. Another great use case for repartition is before you're doing several narrow transformations where you're not shuffling data around. So for example, that filter example we talked about earlier. If you're going to decrease the number of partitions, you should always use coalesce rather than repartition, however, because it will shuffle less data. When you're doing joins and you have skewed data, there are different tricks you can use, and Blake's going to speak to those in a few slides. One of the best places to handle skew is at ingestion time. So for example, if you're doing JDBC reads, you can use Spark options to do partition reads and get performance gains. One thing to know is if you're going to specify one of these options, you must specify them all. And one that's not mentioned here is your fetch size. That's another parameter you can tweak. One thing to know is that the default fetch size actually depends on the database. So it's another area to look into. For these options, what you need to know is the partition column in particular is numeric, and you have to choose it very carefully. You want your partition column to have relatively even distribution. If it's heavily skewed, then your partition read will also have some performance issues. If you don't have a good column that's relatively even distributed, then you can create a partition column through the combination of other numeric columns using addition, mods, and so on. If possible, you want to ask your data owner to include this partition column in the data itself rather than have it generated by the query, again, for performance gains. One example where we saw significant performance was we took a job that was taking 40 minutes to do a read down to under 10. This example is just showing what happens when you do the JDBC read with partitioning. So stride is another area you have to be careful about. It's possible that even if you have a good partition column, your strides will have skew as well. So these parameters generate the queries on the slide. Let's say that your partition mod column had 90% of the data over 900. Then that last query is going to take significantly longer to complete than the remaining queries. So again, you can use tricks like using a hash function followed by a mod to try to get your stride more evenly distributed as well. Another way to work with partition data ingestion is when you're reading in data that is already partitioned. So in this example, we're looking at cloud object storage. Notice that in cloud object storage, our parquets have a wide range of partition sizes. What happens when we read this in is we keep the same partitioning as our source. So to handle that, we read in and we do a repartition to get an even distribution. Another great way to improve performance is through the use of cache and persist. One thing to know is caching is just persisting, but in memory only. If you use persist, you can specify the storage level, and the different storage levels will also have their own set of trade-offs for you to look into. One thing to note is when you do use caching and persisting, you want to immediately unpersist when done to free up memory for garbage collection. So in the picture on the right, we were reading in the same data twice from source and doing a self-join. Without persist, we read in the data twice and do the deserialization twice before we do a self-join. When we persist it, we only have to read in the data once and deserialize one time. So we saw significant performance improvements there. You want to be careful though, because if you over persist, you'll see sometimes extra spills to disk, which will cause issues. You'll see increased garbage collection pressure. And if you have a bunch of things descoped all at the same time, then again, that's going to slow down your garbage collection.
So now I'm going to talk about some different options to try and just easily increase performance of your applications. One of those is if you're doing sequence.forEach to instead do sequence.par.forEach. This allows your for loop to be run in parallel. However, you have to be careful because if you're yielding non-deterministic results, then you're going to create race conditions within your application. So one way to try and do that is to use accumulators or other pieces of the Spark API to allow this method to be thread safe. And then also you want to avoid using UDFs if at all possible, especially if you're not developing in Scala, because everything has to be translated to JVM bytecode. But how UDFs work are they deserialize every row to an object, apply the lambda, and then reserialize it. So by the time it's all done, you're generating a lot of garbage and greatly increasing your garbage collection time. Next, I'm going to talk about some different ways to optimize joins. So I'm going to talk about a couple of different tricks, like how to better pre-process your data, how to avoid unnecessary scans of your databases, how to take advantage of the locality of where your data and partitions are. And then finally, I'm going to talk about a technique called salting. So the first trick is to do what's called a broadcast join. So how broadcast works is it takes the data frame and puts it on every executor. So this trick is particularly helpful if you have a large data frame being joined with a really small data frame. And so in our example, you see on the right, we pull in 2 different data frames, and then you see some exchanges happening and some shuffling happening. And then it's going to sort the data and do what's called a sort merge join. On the right side, we have the same application pulling in the same 2 data frames, but then we broadcast out the smaller one. So you see there's less shuffling and exchanges happening, and then it allows Spark to do what's called a broadcast hash join under the hood, which is much faster than the sort merge join. And one thing to note about this is Spark has an auto broadcast join threshold. So if your data frames are less than 10 megabytes, it's automatically going to be broadcasting them out for you. We like to still specify for it to be broadcast just so we know in our code what is being broadcast and what isn't. So some other tricks you can do is try and filter your data around or down before you actually do your joins. This is particularly useful when you're doing, or when you have data frames that are too large to broadcast. So in our example at the top, we have a medium data frame and a larger data frame. And we're trying to filter out the larger data frame based on the keys in the smaller data frame. And then another trick you can do is what's called dynamic partition pruning, which is going to be out of the box in Spark 3. And what this does is tries to eliminate partitions at read time. So in our example, we have, again, a larger data frame and a smaller one, but not so small we can broadcast it. And Spark is inherently going to try and trim out some of the partitions, and then you can apply filtering tricks as well to try and eventually get those data frames down where you could even potentially broadcast one. So now I'm going to talk about a trick called salting, and it's especially useful if the keys you're joining on in your data frames have skew. So, because if they have skew before they're joined, the resulting data frame is just going to be heavily skewed. So in our diagram at the top, you see there's your dimension key that you're joining on, and it's heavily skewed in just these 4 rows. The arrow represents salting, where we randomize the keys a little bit to reduce that skew. And on the right-hand side, you see the data is more evenly distributed. So one thing to note about this trick is it does take a little bit more time at pre-processing, and it's going to take more memory because you have to salt both your data frames that you're joining on and then map the keys so that you can undo your salting if necessary. Some other things to remember when trying to optimize your joins are you want to always keep your larger data frame on the left-hand side. Spark is going to implicitly try to shuffle the right data frame first. So the smaller that is, the less shuffling you have to do. And then as Kira has already mentioned, you want to take good partitioning strategies, find that sweet spot for the number of partitions in your cluster. And then you want to try and improve the scanning of your databases. So you want to cache and persist, like Kira already mentioned, and you want to filter as early as possible, even in the query, if at all, if you can. And then a big trick to try and do is use the same partitioner across all your data frames, because that's going to increase the chances of the data being on the correct partitioner or on the correct executor. And so it's going to decrease the amount of shuffling the application has to do. And finally, if you see that there are skip stages in your Spark UI, that's good. That means you're doing a great job of optimizing your joins, and things are just going to run faster in the end. So now I'm going to talk about how applications schedule their task. But By default, Spark is set to do FIFO, so first in, first out. But you can change the setting to be what's called fair. And how that works is allows Spark to schedule longer, larger tasks with smaller, quicker tasks. So it increases the parallelism of your application. And it increases the resource utilization. So you're taking full advantage of the cluster you're running on. One thing to note is since things aren't always scheduled in a orderly fashion, it makes the code a little bit harder to debug. So what a lot of people like to do is turn this mode off when they're debugging or running locally and only have it on in their production environment. So when setting up your scheduling, you can also set up what are called pools. And these are basically buckets for the different tasks to go into. And when you're setting them up, you want to take account of the weight and min share of the pool. So weight allows you to set how many resources a pool has relative to the other pools. So it's a way to kind of set priority, because if you give one pool more weight, all the tasks in it are going to finish faster. Min share allows you to say every pool has so many resources from the cluster. And by default, Spark is going to set every pool to a weight of 1 and a min share of 0, so equal use of the cluster, and nothing is guaranteed. You can set all your different pools and their min share and weight in what's called the fairscheduler.xml, and then pass that into your application in the Spark submit. So here I have an example of the exact same application running with the exact same data set and the exact same set of pools too. But on the top, the screen captures of an application where it's just running the default FIFO, and the bottom is in a fair scheduled mode. So you see they both have this long running task. And in the top, the second pool is trying to schedule what it can, and it schedules some tasks, but they're sequential and it's not a ton. And then you have a long gap before the other task, that long task finishes. In the bottom, where it's set as fair, both pools are actually running multiple tasks. And what it's done is allow the application to get ahead of itself while it's waiting on that longer task. So it didn't speed up that task, but it allowed the code to progress even though, and not run anything dependent upon that task.
One of the first resource bottlenecks that you could run into might be memory or network related. In order to tune them, it's important to understand how Spark is serializing your data under the hood. You can use two kinds of serializer, either Java or Cryo. Java is default for most types, whereas Spark sets Cryo as default for RDDs with simple types. So if your if your data frame had columns that were integer or string types, Cryo is being used as a default for shuffling. Java serializer can work for any class and is more flexible, whereas Cryo works for most serializable types and is about 4 times more faster and 10 times more compact. So if you're looking to get some serialization benefits or boost, try using Cryo. Cryo also customizes or serializes custom classes, but in order to make this more efficient, you need to register them with the serializer. So what this does is makes sure that the object doesn't store the class name. So you're saving about 60 bytes if your class name were to be 10 characters, for example. Another gotcha when tuning memory is the lack of use of compressed pointers, or as I like to call them, compressed oops, as the picture of Robert Downey Jr. here. When working with heap sizes that are lesser than 32 gigabytes, you can tell JVM to use 4-byte references instead of 8 bytes. Any object in JVM has a size that is a multiple of 8, making the last 3 bits of its address 0. So what we can use is this, we can use this property to basically allow JVM to do some clever bit shifting to compress and decompress references when loading and finding objects. One thing to note is that the 32 gigabyte heap with 4-byte references can contain as many objects as 48 gigabyte heap with 8-byte references. So if your executor heap sizes are between 32 and 48, you're not getting any memory benefits. Next, we're going to talk about garbage collection, and here are some of the issues that you commonly face when dealing with garbage collection, such as you're having long GC times. There's contention when allocating more objects. You're noticing executor heartbeat timeouts, issues like that. And one of the first things that you can do in order to understand if you're having garbage collection problems is to look at your Spark UI and notice the time that's being spent in your task versus garbage collection. Another metric that we used is to look at our memory on the Kubernetes. So we noticed that our memory was filling up before the garbage collection actually tried to clean up accumulators, and we were noticing long GC times. So the first step when coming to garbage collection tuning is to enable logging. And here we show you two options, two different algorithms, one ParallelGC and one GC. What this allows you to do is understand how frequent your garbage collections are occurring, and some other information as to how much memory was cleaned up, and some other stage-related information according to each individual algorithm, such as minor GC, full GC, and major GC, which we're going to talk about in the next slides. So here we're going to talk about ParallelGC, which is the default algorithm or default garbage collector for Spark. As many of you probably know, the heap is divided into young and old generations. Let's briefly go over some of the things we can do if we were to face issues. If you're noticing frequent minor garbage collection, we recommend increasing Eden and survivor space. If you're noticing frequent major garbage collection, increase young space so that not as many objects are being promoted to old. Or you can try decreasing old space, or increasing old space, or try decreasing what's this property called Spark memory fraction that tells Spark how soon it can evict data frames from cache. Usually, it's not a good idea if you have long surviving data frames that are pending reuse. And lastly, if you're noticing full GC, there's not many things you can do here other than increasing memory or try to increasing your young space. Next, we're going to talk about G1GC algorithm, which is a low latency and highly parallel collector. It works by breaking down the heap into thousands of evenly sized regions so that the GC threads can work on each region in parallel. We recommend this algorithm if you have heap sizes that are greater than 8 gigabytes, and if you're noticing long GC times, which was in our case, we were noticing it. For large-scale applications such as ours, we found setting these properties mentioned in the slide below, the three properties that you see over here, especially helpful. Let's go over a use case where we run the same application with and without these settings. We set parallel GC threads in the second application to 8, which is the number of cores per executor, concurrent GC threads to 16, which is double the amount previously of the previous property, and initiating heap occupancy percentage to 35, which allows GC to be triggered when the heap is filled up about 35%. This setting is usually defaults to about 45%. So what that's allowing you to do is trigger garbage collection early. To paint you a picture, we're going to try and go over the resource differences between the two applications. The first application was hitting our cluster's memory limits and spilling to disk, whereas the second application with these custom settings made it use about 12% less CPU and save about over 200 gigabytes of memory. One thing to note here, though, is that the higher CPU usage correlates to the spill to disk. And lastly, a good mantra to always follow is to collect often and collect early. Here are some of the major takeaways. Performance tuning is iterative and is often case by case. Choose what works best for your situation. Take advantage of Spark UI, logs, and any other monitoring available to you, such as Kubernetes and sysdig in our case. Try correlating these events in your monitoring to your areas of major slowdown, and start working from there instead of tweaking multiple Spark parameters at once. Lastly, you cannot be perfect. As your application and data needs grow, you'll have to do this all over again. Thank you and good luck. Next, we open the room for some questions.